Hello, Mr. Claudia here, and today we're going to teach you how to use periodic functions or trigonometric functions to model some situations in real life. And I really like this topic because there are some really interesting applications of periodic functions in the natural world. These are, remember, periodic means things that repeat or cycle over and over again. So some great ones are looking at the temperature. Now this wouldn't mean the temperature over long term, which we see because of global warming, a steady increase. But this would be like a 365 days, when you look at the temperature over the course of a year. If you look at the sun over the course of a year, I have this sun X joke here, but the angle of the sun in the sky changes over the course of the year, as do the hours of daylight. The moon cycle, that's 28 days, right? The moon changes every 28 days. Tides, which are caused by the moon, this is something that happens every 12 hours. We don't really see it much because we're in an inland part of the country, but this is a big deal if you're on the coast. Circular motion, so things that go round and round, like a Ferris wheel, can also be modeled with a trig function. And vibrations. This is a neat application of this in the real world, in the engineering field. For example, a bridge, as cars go over, it vibrates. Well, that vibration is very small, right? But that vibration can be modeled as a sinusoidal function. So there's a lot of neat applications here. Now, the model that we're going to use to represent, to model some of these real-world situations is a cosine function. We could use sine, but cosine is nice because it starts at 1, like it starts at a peak, and we'll see how that's kind of makes our life a little bit easier. So here's that expression for the model. This is all those translations we looked at in our last lesson. The first one, A, is the vertical stretch. This is also called the amplitude. As discussed earlier, the way of figuring out the amplitude is to take the max, the y max, subtract y min, and divide by 2. B, that is the horizontal stretch, aka the phase shift. Nope, not the phase shift, it's just the horizontal stretch. The trick to figuring this one out, I told you it's easier when we're dealing with sinusoidal functions. We just kind of rewrite the period. So the period is equal to 2 pi over that b value, or 360 degrees over that b value. Next we have C, which is the horizontal shift, or that one's called the phase shift. To figure that one out, I just look at the max point. And you can usually figure it out. For example, if your max point of your data is a tide height of 6 meters, well, then that would be your phase shift, because cos starts at that high point. So you could just figure out, you could just then calculate the angular or the phase shift, and that would be your horizontal shift. We'll look at an example. Finally, the d value is the vertical translation, vertical shift. And this is really a measure of how much that horizontal axis has been moved up or down. The shortcut to figure this out is you take y max plus y min and divide by 2. It's like taking the average. So let's apply this to a neat example. This question shows us the average monthly temperatures in Hamilton, Ontario. And you see like all great Ontario cities, we have a very cold temperatures in the wintertime. Then it warms up, it reaches a really high temperature in July, and then it goes back down, and every year this repeats over and over again. Now let's make so we want to find a model that approximates the data. Finding a model is a nice math way of saying find an equation. But let's make a sketch to try to understand this. I mean, I always like to sketch things, and for the purpose of this question, it can be useful. Okay, so let's sketch. So this is the temperature on the y-axis, and on the x-axis, I guess it would be the day of the year. Now, there are 365 days of the year, so this is going to go up to 365. So let's go 100. Yeah, let's do 50, 100, 150, 200, 250, 300, 350, so it'd be something like that. Day 100, day 200, day 300. This is just a sketch after all. And then we also, okay, the temperatures go down to -5 and they go up to 21, so let's say 25. So 5, 10, 15, 20, 25. And -5. Okay, so let me sketch some of these points. So January 15th, so that would be day 5. Oh, sorry. I guess we're using the middle point of each month. So the middle of January is January 15th. So that's somewhere here. That's a temperature of -4.8. February, it's also -4.8. Day 75, it's 0. Day 106, it's 6. Something like that. 136 is 12. 167 is 18. 22 at 197, so right around here. And then 228 is 20. Blah, blah, blah. I mean, I'm not going to plot them all. I have the lowest point and the highest point. You get a sense of the periodic nature, actually. Well, let's plot the last few. 350 is -2, so it's down here. So you can see, you know, the graph. So we get that shape. And we can understand that this will repeat every year. It's periodic. Now, one thing to note right away is that the data isn't going to be perfect. I mean, it's not a perfect sine wave. We can see that right here. January 15th and February 40, January, middle of January, middle of February, it's the same temperature. Maybe it drops lower. I'm not sure. But there is kind of an understanding that the real world, when you're making a model, the model's not going to be perfect. And that's okay. The model that we're going to use to represent this is the cos, right? The A cos B x minus c plus d. So we have a bunch of things to figure out, a bunch of parameters, a, b, c, and d, to figure out this graph. But really, if you look at it, it's just a cos graph that's been transformed. So let's start by finding these four parameters out using the information above. So first of all, A, that's the amplitude. I find the amplitude by taking my max value, subtracting my min value, and dividing by 2. Okay, well, even though the data is not perfect, I can clearly see in my data that the max point is 197, 21.9, and the min point is -4.8. So I'm going to take, -4.8 as my min point, wherever it is. So I have a max of 21.9, subtract -4.8, and that's divided by 2. Let me get my calculator out and do that. So that's 21.9, 21.9 plus 4.8. That gives me an amplitude of 13.35. Okay, so far so good. The next thing I have to look at is B. Now remember, B is the horizontal stretch, but there's a trick here. You really just need to use this equation. Period is equal to pi over B. So to solve this equation, I need to know what the period is. Remember, the period, the definition of that, is how long it takes for one cycle to elapse. So that would be how long it takes to go from the coldest day to a warm and then back down to the coldest day. Well, regardless of what the coldest day of the year is, the period is 365 days. Okay, I know a few of you are complaining, yes, it's 365 and a quarter because of leap years. That's okay, we're going to assume there's no leap years. So now if I rearrange that equation, B is equal to 2 pi divided by the period. So that gives me 2 pi over 365. And let's just leave it like that. Now we need to find C, the horizontal shift. Now, remember what we said, the the cosine graph is the best, it's the graph we like the most for modeling because the cosine starts at this high point. So then to figure out how far, the cosine usually goes like here. So to find out how far I've moved it, that's my phase shift right there. I just have to look at how the x coordinate has changed. So my max point is at 197. So I would say that my phase shift is 197. Y max is equal to 21.9 occurs when x is equal to 197. So therefore, C is equal to 197 to the right. You guys will know what that means. We'll just have to do that correctly when we sub it into this equation. Now you could have just as easily used the lowest point of the graph and then done a reflection, right? Like the negative cos, and then whatever this point is at. In fact, there's an infinite number of different sinusoidal functions you can write to represent this data. But this I find is the easiest. Just find the max point and the graph has been shifted over by that amount. Finally, we need D. And D is equal to the average, right? So you take the highest point, you add the lowest point or the minimum point, you divide by 2. So my highest value is 21.9. I'm going to add negative 4.8 and divide by 2. Make sure you do the signs correctly, right? So this is actually 21.9 minus 4.8 divided by 2 gives me 8.55. Now you have your parameters. So you are all done. You have your model. Temperature as a function of days is equal to 13.35 times cos, and open bracket, 2 pi over 365 x. Okay, now 197 to the right. So because I'm going to the right, but it's reversed, so it should be minus 197 and then plus 8.55. Cool. So that is part A. It's kind of a neat function. I'm going to put a little box around that. That's so cool because now you can predict the temperature at any day of the year in Hamilton. So what does the question B ask? Estimate a daily temperature on the 200th day of the year. Well, for part B then, you're going to sub in 200. So you get 13.35 cos 2 pi over 365, 200 minus 197 plus 8.55. Now be very, very careful here. Because you use 2 pi when we built up this equation, you have to use radians. You're in radians mode for this. So make sure you've got your calculator set to the right mode. Okay, so it's 200 minus 197. Okay, then I take cos of that. Nope, then I multiply that by 2 times pi divided by 365. Take the cos of that answer. Multiply that by 13.35. And then I add 8.55. And that gives me approximately 21.9 degrees C. Does that make sense? The 200th day of the year would be somewhere after mid-August. So yeah, it would certainly be very cold, very hot. Kind of actually an uninteresting answer. Should have chosen a different day of the year. But anyways, you can see how your model can be used to make predictions. I think this is really neat. There's lots of applications, like I said. And pretty straightforward too, as long as you can remember how to find those 4 parameters for your model. So your homework for this section is page 486, number 1 to 3, A, B only. Hopefully that'll make sense when we do it. And page 487, number 1 to 4. Good luck with that, and we'll see you next time.